So, structural formula. The basic idea we have here is our previous formula we've had. The empirical formula shows you the ratio of the elements in the formula. The molecular formula shows you how many exactly there are, not just the ratio, but the total number of each element in a compound. The structural formula not only shows you number, not only shows you ratio, not only shows you number, it also shows you where the atoms are, like what their physical structure is, where they are related to other ones. And so, so number one, the basic idea of the structural formula is it shows the physical structure of the molecule. It uses bonds to show connections between atoms. And so, to give you an example of how this works, let's take water, good old H2O. And so if I have water, H2O here, if I want to draw the structural formula for this, what I do is I would use bonds to show this. And so the structural formula of water, I have an O, I have two bonds that come out of this, and on the end of those bonds are where my H's are, my hydrogens. So this would be the structural formula of water. That bond, that sort of that line that connects between the hydrogen and the oxygen right in here is those guys right here. Those are your bonds. Basically, what they're doing is that they are basically showing you these two are connected. They're sharing electrons is what's happening. That they have, basically, as they've gotten close enough that they're able to share electrons across there. And so that's the reason why they bond here. So it uses bonds to show connections between atoms. The way this basically works is the number of bonds for each atom is the same as its valence or oxidation number. So if you take a look at oxygen on your periodic table, look at its valence. It has a valence of -2. So because it has a valence of -2, it has how many bonds? It has 1 and it has 2 right there. And so it makes 2 bonds because it has a valence of -2. We don't really worry about the negatives on here. We just look at how many it's going to make. That means it's going to share 2 electrons, and so it's going to make 2 bonds. The hydrogen, the hydrogen has a valence of plus or -1. It has to be +1 in this case. And so it's going to make 1 bond. And so this hydrogen makes 1, this hydrogen makes 1. And so as a result, that works out. And so the number of bonds for each atom is the same as its valence or oxidation number. Let's see. Another way that you might sort of look at this would be to look at CH4. And so if I have CH4 like this, here is one of the ways it would work here, is that to write this out, is to start off with carbon. I have 1 carbon here. Carbon, if you take a look at the periodic table, has a +2, +4, -4 as its valences, is that typically it's going to be -4 for this. And so as a result, carbon will make 4 bonds. And that's just something you sort of just need to know, is that in general, in the vast majority of cases, when you draw a structural formula, carbon's going to have 4 bonds, because it's normally -4. For its valence. And so it makes 4 bonds, that makes it's going to make 4 connections off of it. And so it makes 4 bonds like this. So we have 4 hydrogens attached to that, since it's CH4, and so those 4 hydrogens are just going to go in each one of those bonds. There's 1 hydrogen here, 1 there, 1 way up top, and then 1 over on the side. So if you look at this, then what you can see is that the carbon has 4 bonds, which it wants to, so it's happy. Each of the hydrogens only has 1 bond, so it's happy. We have 1 carbon and 4 hydrogens. So everything's nice and hunky-dory. And so this is how you draw out the structural formula for CH4. Now the next one. Atoms may form double or triple bonds with other atoms in a compound. Is that there are, instead of just having 1 bond from an atom to another atom, it is possible to have 2 bonds. This is called a double bond. Double bonds are much stronger than normal single bonds. They typically result in the atoms being closer to one another. Basically what's happening is that they are sharing 2 sets of electrons rather than just 1. And so a double bond is typically drawn by showing 2 lines rather than 1. Classic example of this is carbon dioxide. And so carbon dioxide, CO2, what happens here, we have 1 carbon and we have 2 oxygens. The carbon wants to have 4 bonds, but only has 2 oxygens to share those with. And so if it only has 2 oxygens, it's going to make a double bond with each oxygen. And so what we'll get is we will get this guy right here. This is the structural formula of carbon dioxide. Does each of the oxygens have 2 bonds like they want? Yes, because oxygen has a valence of 2. Does the carbon have 4 total bonds? Yes, it does, because its valence is 4. And so this would be what carbon dioxide would be. It is also possible to have said triple bonds. Classic example of this is nitrogen. Nitrogen is a diatomic molecule. That is, whenever it's in a free state, it's by itself. You just have nitrogen gas, is that it forms N2. The ones who tend to do this are the elements which have endings in GEN or INE. If the element's name ends in one of those two, then when it's in a free state, it will be diatomic. Hydrogen, when it's by itself, is H2. Oxygen, when it's by itself, is O2. Fluorine, when it's by itself, INE, is F2. Iodine, when it's by itself, is I2. So nitrogen, N2, is this guy right here. Whenever I have two nitrogen molecules, though, if you look at it, it says on the periodic table, I got two nitrogens. They have to bond together. On the periodic table, it tells me that nitrogen generally, we said, has a valence of -3, right? That's its most common one. That means it's going to make 3 bonds. Well, it's only got 2 of them, so that means those 3 bonds are going to be a triple bond between these two nitrogens. And so that nitrogen bond is extremely strong. And so when you're inhaling, as you inhale right now, you're inhaling less nitrogen. That's 70-something% of the atmosphere here. I think it's 78% roughly. You're inhaling a lot of these double-bonded nitrogens. They're really tight together. And this actually is one of the reasons why we have to fertilize soil, is because these nitrogen bonds are so tight, it's very difficult for plants to get the nitrogen that they need. It normally has to happen basically through various biological means if it isn't done through fertilizer. And so we use fertilizer instead to basically get the plants the nitrogen they need without having to break that incredibly strong triple-bonded nitrogen. So it is occasionally possible to have something that has quadruple bonds, but that's pretty rare, and we're really not going to go there. All right, next one up here. It is possible for atoms to have the same molecular formula, but have different structural formula. That is, they have the same number of atoms of each type of atom that's in there, but that when you actually put them together, they actually have a different structure to them. These two types of formula are called isomers. Is that two isomers are ones that have the same molecular formula but have different structural formulas. And so this is something that you ought to be a little aware of, because if you say like they're making a particular drug, is that you can have two different drugs that have exactly the same chemical formula. They have exactly the same molecular formula, but they do two completely different things because their structures are different. In the same way that, I can take a cannon and I can use it to fire it at someone and do damage to someone, or I can take those same pieces and turn it into a flower pot. It does two completely different things depending on what you're doing with those based on how the structure is. Same parts, different structure. So I have sort of some examples down here of two different molecules here. And if we take a look at each one, you can sort of see on this first one, let's count the carbons. We have 1, 2, 3 carbons right there. So we know this is going to be C3 something. We have hydrogens. We have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So H8. And we have just one oxygen right here. So just O. So that's C3H8O. Then we have a different structure over here on the right. Let's count the carbons. It has 1, 2, 3. So C3. Then the hydrogens, it has 1, 2, 3, 4, 5, 6, 7, 8. So H8. And it has one oxygen, O, right here. And so C3H8O. It has exactly the same molecular formula as does the first one. These two are both identical, therefore, but these guys have different structures. So these are isomers. Turns out the one on the left is a type of propanol, which is an alcohol. The one that's on the right is not propanol. It actually is a type of ether. It is one that could be used, say, as an anesthetic. It would knock you out if you had to inhale it there. These two chemicals have two completely different properties despite having the exact same molecular formula, C3H8O. That's because they have different structural formula. They are isomers.